So a very good day once again. Here we have quantum electronics part 4. So in our last class, you remember that we introduced quantum wells. So we'll just speak through and see how far we'll be able to go. So in our last class, we made mention of a few applications of quantum wells, some applications. And there we said, well, one of those applications is in lasers, okay? And we're able to mention that in lasers, the quantum wells are used to reduce the threshold current required to initiate lasing. And as such, we are able to make devices that are more energy efficient. So here, the confinement of the carriers allows for faster response time. Making quantum wells or quantum well lasers rather suitable for high-speed communication. Then we also made mention that quantum wells are used for the fabrication of photodetectors. And these are used for detecting light with high sensitivity and selectivity, okay? And then we also made mention of high electron mobility transistors, high electron mobility transistors. Call this HEMTs. Okay. So here, quantum wells are used to achieve high electron mobility, leading to faster electronic devices. Okay. And then we also use them in solar cells. Okay. So the quantum well solar cells have the potential to achieve higher efficiency by utilizing multiple quantum wells to absorb the broader spectrum of light. So we can actually go on and on. And what is a quantum well? We made mention of this, that when we have different materials, you know, especially the composite semiconductor materials meshed together, like in the case of having gallium arsenide here, gallium arsenide here, then let's say we have indium gallium arsenide, then we have this deformity. So this deformity is such that should electrons get into this confinement, then we want to observe their interaction. And because we now have boundaries, this is a boundary, this is also a boundary. So we now have to investigate how this wave function that characterizes this microscopic particle behaves as it moves between these mediums, for which this particular height of deformity is given as the potential, the well potential. So we want to investigate the relationship between this and the energy of this particle. So now we also want to check if when E is greater than V and when V is greater than E, what will happen? So if this energy is greater than the potential voltage, or let's say the potential, let's put it that way, the potential energy rather, then the particle will have sufficient energy to escape this confinement. And what happens if it's less? And then what now happens to the energy ratio? And then should the particle move between these barriers, what will happen? We also understand from, we already described the de Broglie wave where we're able to investigate the wave particle duality. So we also know that when a wave propagates through a particular medium into another medium of different material property, there you begin to talk about the dielectric constants, the permittivity, permeability, and all of those properties, which we made mention of when we introduced the electromagnetic wave concept. You agree with me that in as much as the incident wave will penetrate, there will be an amount of wave that will be reflected, while an amount of wave that will be transmitted. Okay? So now we are going to compare, we are going to investigate these components, okay, and then formulate develop a proper formulation for the wave equation, and then solve the Schrödinger equation relative to what we have here. Okay. So, and for us to do that, then we will have to define the boundary conditions, okay? So here, this is a boundary, okay? This is a boundary. So what happens to this wave at this boundary? And what will happen to it at this boundary? Should this be region 1, region 2, and region 3? Okay. So for us to be able to appreciate this idea, we will have to first of all provide a formulation for the probability distribution function. Okay, we have some questions here. So are we to commit all the field equations to memory? Please, there are all too many just in case. Okay, field equations to memory. This is coming from Piggyback. I really don't understand what you mean by field equations, because we've not really handled multiple equations since we started. All we've been talking about, the only equation we've been relating with is the Schrödinger equation. And as far as I know, that is one. So how we get to manipulate it does not translate to multiple equations. So maybe you clarify, and then we'll pick that again, okay? Yeah. Okay. So let's move on then. Now, if you've looked through the previous notes, I will just run through so I don't have to waste much of our time. Then let's assume we have a potential heel. This is a heel where V at this point is the same as 0. And then at this point, we are going to overcome this heel with the energy E, which has to be greater than V, because this is the potential of this wheel, of this heel. Or we could actually have a potential slope. Now, I just call this a slope largely because I have not completed the other part. So else it would have been a well, more like a valley, okay? Now, at this point, V is the same as 0. And then at this point, we have E, okay? So if at this level, this is x being the same as 0. What happens as we progress, as x in this direction, as x becomes greater than 0? And now, within this slope, we can tell that we have a negative potential. Now, if this is 0, if v is the same as 0, anything underneath will be negative v0. And at this point, you will observe that we have a positive potential. This is v0, anything above it will be positive, okay? So here we can say that this is greater than v, and at this point, this is greater than v, okay? So having this, we have two regions here. This is region 1, and this is region 2. Same here, this is region 1, this is region 2. So technically, the potential of this step up and step down can be defined as v of x, for which we could have 0 in region 1 when x is less than 0, and then we have v greater in region 2 when x is greater than 0. Okay? Because here the potential is 0 at x less than 0, because this is x less than 0 at this point. This is x greater than 0, while this is x, okay? So the idea is that we want to tell what happens to the state of the particle passing through a boundary between this potential region, from region 1 to region 2, irrespective of the fact that it is either a step up or a step down, okay? So now you already know that the probability of finding a particle within that volume is given as the integral taking limits from negative infinity to positive infinity, because now we have to deal with negative to positive values given x, right? Then should we integrate the probability density function, which you already know? Let's place this psi of x, then the x. The probability of finding a particle within that region is 1. So this implies that the wave function must be continuous, okay? So the implication of this is that the implication is that the wave function psi, the wave function must be continuous. Okay. Now, if that is true, then we can now define or describe the boundary conditions. So if the wave function must be continuous, then it means that the wave function coming from this region, psi of 1, must be the same as the wave function in region 2. That's the idea, if it is continuous. So technically, this now helps us define the boundary conditions. So the boundary condition 1, boundary condition 1 is that the wave function in region 1 at x equal to 0 t is the same as the wave function in region 2 at x equal to 0 t. This is very important. So I'd love you to just look through. Some of you must have watched the videos, but just pay attention, please. Real attention. And from this, we know that for this particular equation to be satisfied, the wave function on both sides of this potential step up or step down, the wave function on both sides of this boundary must have the same time dependence. So that is, if you recall, the time dependence, which is the solution of this Schrödinger equation, is the same as psi of st, psi of 1, which is psi of est epsilon minus j e over h cross t, if you remember. And now, based on the boundary condition 1, and based on the fact that we've been able to resolve the total probability density function to state that the wave function must be continuous irrespective of the boundaries, then this must be the same as the wave function in region 2, s of t, which is psi of 2 e s epsilon minus j e over h cross t. So at x equal to 0, with the same amount of energy E, which means the total energy must be conserved. And E is a constant of motion across the boundary. Because when x is equal to 0, and then we are going to have E in this case. But you should note that this state function in the first region must be an eigenfunction. This, that is psi of, let me please put this. Now, this state function must be an eigenfunction psi e of st of the Hamiltonian corresponding to the eigenvalue. The eigenvalue, this corresponds to the eigenvalue E, which is the same as P naught squared over 2m with time dependence, this with time dependence, this, which is epsilon minus j e h plus t. Now, the continuity of wave function across the boundary is an important basic boundary condition on all wave functions in quantum mechanics, okay? So you don't want to forget this, okay? Now, if we consider the boundary condition on the partial derivative of the wave function, okay? We want to consider the boundary condition on the partial derivative of this function. Now, that is the psi e of x divided by the x. We want to resolve this. But you should recall that the wave function must satisfy the time-independent Schrödinger equation. And as such, it can be integrated over an infinitesimal range. Now, rather than take x from 0 to, say, d, so rather than take x from taking on values from 0 to d, now, for the sake of symmetry, we'll rather take from negative d over 2 to d over 2, which is also the same as 0 to d. Now, when we begin to resolve the wave function in a well, we will recall this for the sake of symmetry, okay? For the sake of symmetry, we want to use this. So if we now consider an infinitesimal range, you know, something probably between this point to this point, okay? So then we should be able to estimate that should x be equal to 0 at this point, then for that infinitesimal range, the delta, then at this point, we can say that this is negative delta over 2. And at this point, this is positive delta over 2, considering that infinitesimal range, this range, okay? So when we do that, then we should be able to integrate the Schrödinger equation over this range, so that we now have the integral negative delta over 2, positive delta over 2, negative h cross squared over 2m, d squared dx squared plus v of x psi of e of x dx. We are integrating, and this is going to give us e, because we already know that now this is a free particle moving at a constant velocity, with a constant velocity rather. So since E is constant, it's a constant of motion rather, you will recall someone asked that in our last class. Then this potential operator reduces to 0, okay? This is going to reduce to 0. So what we are going to be having here is going to be the integral of this expression, okay? So that we now have this negative delta over 2, positive delta over 2, then psi e of x dx. In this case, E is this quantity, the kinetic energy, okay? Because the particle is moving with a constant velocity. So the potential energy operator is the same as 0. And once this is resolved, we now have negative h cross squared over 2 into bracket 1 over m d dx psi e of x, then for which x is negative delta over squared, then here x is positive. S is the same as positive delta over 2. Okay. Now, in the limit that delta tends to 0, then the boundary condition will become 1 over m1 d dx psi 1 e of x at x equal to 0 will be the same as 1 over m2 d dx psi in the second boundary or region of x at x equal to 0. Now, this is equally an important parameter. And you recall that the arbitrary wave function can be expanded by the superposition of the eigenfunctions with the Hamiltonian, for which this is the solution, okay? And then we can begin to add up for each energy level, okay? Now, I don't want to go that route now, but you will observe that the corresponding derivatives of any linear combination of the eigenfunction must satisfy this expression. This particular expression we just derived, this expression. And then, one thing that requires attention here is the reciprocal of the mass of the particle in both regions, 1 over m this. Okay. This requires some attention. Okay. You observe we have this. So technically, when the effective mass, m, of the particle does not change across the boundary. So let's assume the the mass of the particle does not change as it moves from boundary 1 to boundary 2, then the derivative of the wave function must be continuous across the boundary. If it's the same, but if it changes, then it won't be continuous. We are going to have different values. But should the mass be constant, then this parameter will be equivalent. Then we will be able to now describe the second boundary condition, which will now be, should we knock this off, then the second boundary condition 2, will now become d dx psi 1 st at s equal to 0 is the same as d dx st. And don't forget that the assumption here is that the effective mass of the particle does not change as it moves from one region to the other. Okay? So technically, when the effective mass of the particle changes across the boundary between the two potential regions, such as across a heterojunction between two different semiconductors, like we have in the composite semiconductors like gallium arsenide and some others, then it is the partial derivative of the wave function divided by that effective mass that must be continuous. Okay? So we don't want to go that route now. But so far, we have been able to describe the two major boundary conditions, which are that the wave function in the first region is the same as the wave function in the second region, and the first time derivative of the wave function in the first region is the same as the first time derivative of the wave function in the second region. So these are the two boundary conditions we are going to be invoking from time to time to resolve what we want to do. But now, we already know that the particle cannot be stored or accumulated in an infinitely thin boundary. We made mention of that when we reviewed the electromagnetic wave concept. So the probability current, J, being the number of particles through a boundary per unit volume per unit time, must therefore be given as the gradient, or better still, the divergence of the probability current will be the same as the negative d rho dt. And now we already know that that this rho is the probability current density, right? Is the current density rather. So if it is the current density, then we already know that d dt will now be the same as the PDF. Where the PDF, this expression is the same as rho, right? Rho square is the same as rho, which is the probability density, where J is the probability current, right? Probability current, while rho is the probability current density, right? So now that we have been able to resolve this, we also know that this is the same from all we've been doing so far, is the same as negative d dt psi sigma. Well, let's just RT psi RT, right? So it's the same thing. all in brackets. Yeah, so that's the same. So what do we now do? Then we now have to resolve this. Now, if we differentiate this, this is a product rule. So U dv, then V du. This is what we've been doing so far. Then we also know that this divergence of J, this nambla is the same as d dx, right? In this case, where we can say this is in the x direction. So in one dimensional case, for instance, okay? So if we want to consider in 3 dimensions, then we're going to add plus d dy plus d dz, right? It's more like getting the gradient. Now, your vectors. So going by that, we can now resolve that this expression is the same as the j sub x dx, which is the same as nambla of that expression, okay? Or the divergence of that expression. Now, then we now have the j sub x, the x, will now be, so once we integrate this and multiply by this, so we now have a negative here, negative psi of x. So let's say in the x direction, so this arrow reduces to x, right? It's now x of t d dt psi s, because here we have the t, right? Of t minus psi of st d dt psi conjugate st. So if we now apply the time-dependent Schrödinger equation to this expression, what are we going to get? Now, we already know that this is a free particle. So the Schrödinger equation, which is given by j h cross the psi, the t, is the same as negative h cross squared over 2m, the square psi, the x squared plus v psi. So this expression reduces to 0, right? So all we have is this. So that when we resolve this, then we have to figure out the psi dt. The psi dt. We should make the psi dt the subject of formula here. And then once we plug that into this expression, then we can now go on to solve. Well, we already did this in our previous lecture. Well, let's just review it again. So this is going to give us the psi. The t will be the same as we divide by this 1 over j h cross times negative h cross squared over 2m, the squared psi, the x squared. And once we rationalize, that's times j squared. So this is going to give us negative j over h cross minus times minus j h cross squared over 2m, the square psi, the x squared. Minus times minus, so that's going to give us plus. So the psi, the t, is going to give us j h cross over 2m, the squared psi, the x squared, and then the conjugate will just be a sign change, right? So that becomes negative j h cross over 2m, the square psi, the x squared. So once we plug this into this, then what do we get? Then the j sub x, the x, will now be the same as negative j h cross over 2m psi conjugate st, the squared, the x squared, psi st, plus, because this conjugate, this process is negative, so negative times positive, that's negative times negative, that's positive. So that'll be J H cross over 2m psi of st d squared psi conjugate st dx squared. Okay. And now this is going to be the same as the j sub x dx. So if we bring out d dx, so that will give us d dx into bracket minus j h cross over 2m psi conjugate st, then d dx times d dx will give us this psi xt plus jh cross over 2m psi st, then d ds psi conjugate st. So you observe that this parameter, and this parameter are the same, and then j is the same as this, j sub x. So then we can now say that the probability current J is the same as negative J H cross over 2m psi conjugate st d dx psi st plus J H cross over 2m psi st d ds psi conjugate. Okay. Now, is this clear, please? Where this is the probability current, right? Okay. So now that we have resolved this, we can now move on to define some other parameters. Well, I'll just move on quickly, okay? So in quantum mechanics, if we want to know the state of the particle, it will be necessary to compute the wave function of the particle from one region to the other region. And you should know that energy is conserved, as we have already evaluated in this case. So that the total energy is a constant of motion and is the same in both regions. So hence, the wave function must be an eigenfunction of the Hamiltonian of the particle corresponding to the energy, which is now described as the kinetic energy. That is E, because it's a moving particle, so it's the same as half mv squared, right? Now, it means that the Hamiltonian operating on the wave function is the same as E psi E of x, because the Hamiltonian is a function of the kinetic energy. And then in the Schrödinger equation, we already know that the Hamiltonian operating on the state function, say in one dimension, is the same as negative h cross squared over 2m d squared dx squared plus v of x times psi e of x, which is the same as e psi e of x. And with this, you will observe that the wave function will give us a second order differential equation. So let us try to resolve this quickly. So I'm going to wipe this so we need more space. So we already know h cross psi of x is the same as negative h cross squared over 2m d squared dx squared plus v of x is now psi E of x is the same as E psi E of x. Now, if we rearrange this, we have that E psi E of x. Okay, let's just open it up to clear all doubts. Let's just open it up. So let's open this up. So this is negative h cross squared over 2m the squared psi E of x dx squared plus v of x psi E of x. We just open up the bracket, and then this is the same as E psi E of x. So if we move this across the equality sign, so that will be E psi E of x minus v of x psi E of x is the same as negative h cross squared over 2m the squared psi E of x dx squared. So in this case, we have E minus v of x times psi E of x is the same as negative h cross squared over 2m the squared psi E of x dx squared. Okay. So this is now going to give us the squared psi E of x dx squared will be the same as negative once we multiply by 2m and divide by, so that will be 2m and divide by h cross squared times E minus v of x psi E of x. And you'll observe that this is a second order differential equation having the form the squared psi E of x the x squared equal to negative k squared psi E of x, where in this case k squared is the same as 2m E minus v of x divided by h cross squared, okay, which is the wave number. Now, k will be the same as the square root of this process. Square root of h cross square will be h cross. So that will be square root of 2m E minus v sub x over h cross. So you observe that in region 1, so in region 1, let's say region 1, v sub x in our previous diagram is 0. So that if v sub x is 0, then the propagation constant, which is the same as the wave number, will reduce to 2 square root of 2me over h cross. And in region 2, v sub of x is the same as v. Then the propagation constant will be the same as the square root of 2m E minus v over h cross. So now, what happens when the energy of the particle is less than the potential of the well? Then the imaginary part, k, will now be replaced by alpha, so that k will be the same as j alpha, such that alpha will now be the same as the square root of 2m v minus e over h cross. Okay. So if this is clear, we now want to resolve what happens in the boundary. Okay. Now, if this is clear, okay, so we just played with what you already know and then move from our first order to our second order. meaning rewriting the Schrödinger equation in the second order. So this is the same as the Schrödinger equation, okay? This is also the Schrödinger equation, but written in the second order, okay? Derivative form. Okay. Now, recall we are dealing with a well that looks something like this or that looks something like this. And we're able to describe the potential of this well, V of S, to be described as either 0 or V greater, such that in region 1, we have S less than 0, and in region 2, we have X greater than 0. So when a beam of, say, mod square of a particle per unit length is incident on the boundary at X equal to 0, this S equal to 0. So a particle is incident at this point. This particle comes at this point. It's at this point, that particle, okay? At S equal to 0, from region 1 is moving. So the solution now becomes this. Now, this is what I want you to pick from this. So when the particle comes in here, recall that we have this potential here gives us information about the material difference. So from your understanding in optics, when we have a wave incident upon this material, this incident wave, now we know that we are going to have two components on the other side based on material difference. One will be the reflected wave, and the other will be the transmitted wave. So the wave that we reflect back into region 1, and the one that goes into region 2. So this will now help us describe the system of equations that describes the wave function. Because now this is the wave, is incident, this incident, then we know we are going to have a reflected wave, and then we are going to have a transmitted wave. So hence, we are going to have two systems of equations here, such that one of the equations will describe the incident and the reflected component, while the other equation will describe the transmitted component. And don't forget that this is region 1, and this is region 2. This is region 1, and this is region 2, okay? So then we already know that the wave function must be continuous. So what we now have here is that the wave function from region 1 will be the same, having the solution of the incident wave A, J, K1X, plus the reflected wave, say B, having a magnitude of B, epsilon, minus. Now, both the transmitted, the incident, and the reflected wave components are equal, but the difference is the direction. So while one is traveling from left to right, the other is traveling from right to left. And as such, we have this negative sign to tell the reflected wave. J, K1, they have the same wave number because it is the same wave that impinges on this boundary that is reflected back. Then X. And then the second equation follows directly, which describes the transmitted wave that goes into the medium. F X will be the same as C epsilon J K2 X, because this wave is from region 1 and is reflected back, but this wave is now in region 2. So the wave number that describes that is K sub 2. So this now is for X less than 0, that's at this point, and to this boundary. And then this expression is for x greater than 0 at this point. So, like I mentioned earlier, this component is the incident wave. Incident wave. This is the reflected wave. And then this is the transmitted wave. But we already know that the wave number is the same as the momentum divided by the reduced Planck constant. And we also know that the momentum is the same as the mass times the velocity. And the Hamiltonian is described strictly by the energy, which is the kinetic energy in this case. And that is m squared over m dot v squared over 2. So that E is the same as mv squared over. Then mv squared over 2m, which is p squared over 2m. And then we have that E is the same as p squared. Then we have P will be the same as 2m. So technically, we can now say that K1, in this case, K1 is the same as the square root of ME over H cross. Like we mentioned earlier, we already showed that. While K2 is the same as square root of ME minus V greater divided by H cross. We already showed this. And then we also showed that when E is less than V, then K is the same as the imaginary component, J alpha, such that alpha is equivalent to K is the wave number, you know, when the potential is larger than the energy of the particle minus this divided by H cross. But the point now is this. We have these two equations. We have to resolve them. And for us to be able to resolve them, we have to apply the boundary conditions. Okay? So this brings us to the boundary conditions. Now, for us to be able to do this, so we're going to just represent this again. Let us rewrite these equations. Let's write this. We have side 1 of E is the same as epsilon j k1x plus b epsilon minus j k1x and psi of E, yes, is equal to C epsilon j k2x. This is for x less than 0, and this is for x greater than 0. Okay. Now, for us to be able to resolve this, let us apply the boundary conditions. Now, recall that the boundary conditions are that the wave function must be continuous. So that's the first. And then the first time derivative of the wave function in region 1 and the first time derivative of the wave function in region 2 should be the same. Okay? So if we now apply these boundary conditions, on this system of equations, what do we get? So when we have the wave function in region 1 to be the same as that in region 2, then it means that A epsilon j k1x plus B epsilon minus j k1x is the same as C epsilon j k2x. Okay? So if that is clear, then we can now resolve this further. Okay? At the boundary where we have this, at this boundary, at x equal to 0, at x equal to 0, x equal to 0, x equal to 0. So we are going to have epsilon 0 will reduce to 1. So we're going to have A plus B is equal to C. So let's call this 1 star, for instance. Okay? And then we can now also evoke the second boundary condition, which is the first time derivative. That's the first time derivative of this is the same as the first time derivative in the second region. So this is equivalent to d dx psi 1 of x is the same as d dx psi 2 of x, right? And now when we take the first time derivative of this, what do we get? That will be a k1, that will be a k1 epsilon j k1x plus b k1. Now that will be minus because of this negative. So that will be minus b k1 epsilon minus j kx is the same as c k2 epsilon j k2x. Okay. And in the same vein, should we consider at this boundary, then x reduces to 0, and this expression reduces to 1 epsilon of 0. So we now have a k1 minus b k1 is the same as c k2. So this is our second equation. So let's call this 2 star. So now we should be able to resolve these two simultaneous equations. A k1 minus b k1 is equal to c k2. So once we resolve these equations, then we should be able to provide the system of equations for the incident wave amplitude, because now we have, this is the amplitude of the incident wave, this is the amplitude of the reflected wave, and this is the amplitude of the transmitted wave, okay? So by the time we plug in this into this, so that will be A K1 minus B K1 will be the same as A plus B K2. So this is A minus B, right? K1, right? Is equal to, okay, no, let's expand that. Let's not go that way. We'll do that when we try out the second one. So this will be the same as AK1 minus BK1 will be the same as AK2 plus BK2. So if we collect like terms, so that will be AK1 minus AK2, which will be the same as BK1 plus BK2. So that will be A into bracket K1 minus K2 which is same as B into bracket K1 plus K2. So the ratio of the reflected wave to the incident wave will therefore give us K1 minus K2 over K1 plus K2. Right? And that is pretty straightforward, right? And then we already know our K1, we know our K2. So once we plug them in, then we should be able to resolve that, okay? Now, let's just work that out quickly. Let's work that out. So we already know now that B over A is the same as K1 minus K2 over K1 plus K2, which will be the same as square root of 2ME over H cross minus square root of 2M E minus V greater divided by H cross over square root of 2ME over H cross plus square root of 2M E minus V greater over H cross, right? So this now will be the same if we collect like terms. Square root of 2M, let's just take 2M over H cross into bracket square root of E minus square root of E minus V greater divided by square root of 2M over H cross into bracket square root of E plus square root of E minus V greater, right? So this can truncate this. So B over A is the same as square root of E minus square root of E minus V greater divided by square root of E plus square root of E minus V greater. Okay. So that's that. And then we also know from our deduction that B is the same as C minus A. Okay. And then this will now give us K1 A minus K1 B is the same as K2C, okay? And this now is going to give us K1A minus K1C minus A, the same as K2C. So K1A minus K1C plus K1A is the same as K2C. And this is the same as 2K1A, which is the same as K1C plus K2C. So 2K1A is the same as C into bracket K1 plus K2. So the ratio of the transmitted wave to the incident wave is the same as 2K1 over K1 plus K2, okay? And then we already know that K1 is given as square root of 2ME over H cross divided by square root of 2ME over H cross plus square root of 2ME minus V greater divided by H cross. So this is going to give us the same as 2. Okay, let's just, let me do it this way. Square root of 2M over H cross into bracket 2 root E divided by, to collect like terms here, root 2M over H cross into bracket square root of E plus square root of E minus V greater. So this can take care of this. So this becomes 2 root E over square root of E plus square root of E minus V greater. Okay. So now you'll observe that we have two ratios, okay? B over A and C over A. The ratio of the reflected to the incident and the ratio of the transmitted to the incident wave. Okay? Here, these are the amplitudes, right? So the transmission coefficient and the reflection coefficient, C and R, can now be deduced. Now we know that the transmission coefficient is the probability current of the transmitted wave ratio of the probability current of the transmitted wave to the probability current of the incident wave. And now this is the same as K2 over K1, which is the wave number in medium 2 over medium 1, because it's in medium 2 we have the transmitted wave, and in medium 1 we have the incident wave, times this ratio of the transmitted to the incident wave squared. So now this is going to give us, okay, so we can quickly walk through that. Now this is now going to give us K2 over K1 mod 2K1, which we just showed, K1 plus K2 all squared. And this is going to give us T to be the same as mod K2 over K1 times, this is 4 K1 squared over K1 plus K2 all squared, right? So this can truncate this so that we now have this to be the same as 4 K1 K2 K1 K2 divided by K1 plus K2 all squared. Okay. And once that is done, we can now plug in the parameters for K1 and K2. So this will be 4 square root of 2ME over H cross dot square root of 2M E minus V greater over H cross divided by square root of 2M E over H cross plus square root of 2M E minus V greater divided by H cross all squared. Okay. And then we can also rewrite this as T to be the same as square root of 2M over H cross, that's for this expression, times square root of 2M over H cross for this other expression, into bracket 4 square root of E dot square root of E minus V greater, right? Over square root of 2M over H cross all squared, because this is all squared here, right? Into bracket square root of E plus square root of E minus V greater all squared, right? So from this, you can see that this is the same as square root of 2M over H cross squared over square root of 2M over H cross squared. That's this. So this will truncate each other. So all we now have is 4 square root of E times E minus V greater divided by square root of E plus square root of E minus V greater. Or squared, right? This is squared. So T therefore is the same. So should we write this? So T, the transmission coefficient is the same as this. And then if that is clear, then the reflection coefficient R is the probability current or the reflected component of the probability ratio of the reflected component of probability current to the incident component, incident. So this will give us mod B over A squared, which is the same as we already know. This is K1 minus K2 over K1 plus K2 all squared. And then we already derived this, and we know that this is square root of E minus square root of E minus V greater divided by square root of E plus square root of E minus V greater, not squared. Now, you will recall from Kirchhoff's current law, KCL, that the total current into and out of a boundary is conserved. It's always the same. So current into a node is the same as the current out of the node. So hence, the sum of the transmission coefficient and the reflection coefficient must be the same as 1. This is regardless of whether the energy is greater or less than the potential. Therefore, no particle can accumulate in the thin layer. Okay, so no particle can accumulate here. That's the idea. So it's either it is transmitted or it is reflected. So in other words, R can never be equal to 0. So the reflection coefficient can never be equal to 0. It must have some value. That is, no particle can never have 100% probability of going through the sharp boundary T equal to 1. Okay? So now, this brings us into an important metric because it now means that should we have a boundary and a wave transmits into this, so there's the possibility of it reflecting back, okay? So should it be incident this way? So it goes in, then it begins to go back. Then we try to go in again, then it goes all the way, and then begins to come back. And it goes in, and then goes all the way, and then begins to come back. And then we see this gives us some kind of curve like this. Okay. Where this is the probability density function in region 2. Okay. And here, x is equal to 0. This is x. This effect is what we call the tunneling effect. But, well, don't worry, we'll come to that shortly. So the implication of the wave function is that the number of particles in region 2, this is region 2, decreases exponentially. It decreases exponentially with distance from the boundary x equal to 0, which is the quantum mechanics effect. So that is in region 2, there are as many particles going in the positive x direction as there are going in the negative x direction. Or every particle that penetrates into region 2 turns around and heads back to region 1. So this implies that there can be no net current flow in region 2. So that T, the transmission coefficient is 0 and R is equal to 1. But there's a caveat. You should know that there are still particles in region 2. Since the probability distribution function of finding a particle in this region is still equal to 1. It's not 0. Okay? So, if there's another layer or surface separating region 2 from region 1, then we now have something like this. So this now brings us into the quantum well description. Okay? And now I will just try to run through quickly. Now, in the case whereby we now have something looking like this well, where we have region 1, region 2, region 3. So it means that we are going to have 3 systems of equation, because there is the incident wave, and here we know we have this incident from region 1. Then we're going to have a reflected component for region 1, and then we have a transmitted component, which is in region 2. So this gets to this point and becomes the incident wave. This is transmitted, right? This is transmitted. Where this now becomes the transmitted, this is the transmitted in region 2. So we now have reflected. This is reflected in region 2. And then we have the component that goes into region 3, transmitted in region 3. So the same way we described the previous example, we can now develop the system of equations for the wave function. And psi 1 E of x will be the sum of the transmitted, of the incident component rather, jk1 of x, which is this, plus the reflected component b, epsilon minus j k1 of x. This is for x less than 0. But at this point, we want to say this is x equal to 0. Well, don't worry, we'll come to that shortly. We'll still come to that. So just want you to get the reasoning for now, okay? So we'll come to symmetry. Let's just, let's leave it the way we have been taking it. Then here we have in the second region now, we have psi of E of x will be the same as the incident, which is C, epsilon j, k2, this time x, plus the reflected, say D, epsilon minus j, k2x. This is for 0 less than x less than D, if this is 0 and this is D. And then psi in the third region, so it will be the transmitted component, epsilon j k3 of x. And we know, going by what we have analyzed so far, already analyzed, that the wave numbers k1 will be the same as square root of 2me minus v1, all things being equal, h cross. Then k2 will be the same as square root of 2m e minus v2 over h cross. And then k3 will be the same as square root of 2m e minus v3 over h cross. And now we have to solve this system of equations in this regard, okay? So for us to be able to show that the solution so as to resolve our transmission coefficient and the ratios between the reflected and the incident and the transmitted to the incident wave, we also apply the boundary conditions, okay? Now, Recall that the boundary conditions we have is that the wave function in region 1 at 0 is the same as the wave function in region 2. We have this. So it means that this and this will be equal, right? And then it means that A epsilon j k1x plus B epsilon minus j k1x will be equal to C epsilon j k2x plus D epsilon minus j k2x. So at x equal to 0, so what we now have again, so this reduces to 0, so we now have A plus B is equal to C plus D, just the same way we did what we did earlier. Now, if we take the first time derivative, the psi of 1 e the x at x equal to 0 being the same as the first time derivative in the second region, the s equal to 0. So it means that this now, if we differentiate this, so we have A, K1, let's say J, epsilon, J, K1 times 0, right? Because S is 0, minus J, K1, B, epsilon minus J, K1 dot 0, because we already know that X is 0, will be the same as that in the second region, J, K2, C epsilon J, K2 dot 0, minus J, K2, D, epsilon minus J, K2 dot 0. So we now have J, K1A minus J, K1B, which will be the same as J, K2C minus J, K2D. So this is the same as K1 into bracket A minus B, which is the same as K2C minus D. So we have the first equation here, then we have the second equation here. So if we now apply the boundary condition at D, at S equal to D, so we applied at X equal to 0 here at X equal to 0. So at X equal to D, what are we going to get? So I'm going to wipe this, so we retain what we have here. So let's wipe all of this. So now we want to check at D, not at 0, okay, for the first boundary condition. So we are going to have between 2, because now at D, we are dealing between 2 and 3, right? Region 2 and region 3. So 2 and 3. So that's going to give us C epsilon J K2 D, where S is now D, plus D epsilon minus J K2D is the same as F epsilon J K3D. Okay? And now, if we now resolve, so this is our, how many equations we have now? Okay, this third equation. Now, if we also take the first time derivative, the x at x equal to D being the same as first time derivative E in the third region, the x at x equal to D, then we have, if we differentiate this, so we have JK2 C epsilon J K2D minus J K2 D epsilon minus J K2D equal to J K3 F epsilon J K3D. So this would be K2 into bracket C epsilon J K2D minus D epsilon minus j k2d, which is k3 f epsilon j k3d. So now, by solving the system of equations, so from 3, we have this, then we have this as 4. So this now can be written as two equations. And when we add and subtract, I'll just run through quickly. We are now going to have C epsilon j k to d plus d epsilon minus j k to d plus C epsilon j k to d minus d epsilon minus j k to d, which will be the same as k2 f epsilon j k3d plus k3 f epsilon j k3d. Okay. And when we multiply through, let's say we multiply through by epsilon minus j k3d, then we are going to get C epsilon j k to d plus d epsilon minus j k to d equal to f epsilon j k3d. Then we are going to have k2 C epsilon j k to d minus d epsilon minus j k to d is k3 f epsilon j k3d. So by the time we solve, so let's solve for C and D, then we now see that C is the same as f epsilon minus j k3d over epsilon j k to d, and D will be the same as f epsilon minus j k3d over epsilon minus j k to d. Hence, f, which is the amplitude of the transmitted wave, will be the same as a epsilon j k3d over cos k2d minus j k1 squared plus k2 squared over 2k1 k2 sine k2d. And once we take the ratio of both components, then this comes this way, and we get the factor. And in order to derive the transmission coefficient T from this expression, we need to interpret the expression for the ratio between the transmitted wave function to the incident wave function. And then we'll have to relate it to the transmission coefficient in the context of the potential step or barrier in the in quantum mechanics anyway. So one other thing we should note now is that in quantum mechanics, the transmission and reflection coefficients for a particle encountering a potential well or step or barrier, as we may put it, are typically derived from the continuity conditions, like we already showed for the wave function and its derivative. So here we already know K1, K2, K3 as documented, and then to identify the relationship to the transmission coefficient, we should know that the transmission coefficient T can be related to the ratio of the amplitude of the incident and transmitted wave. Okay? So typically, if we have, say, the wave function described by, let's put this, A epsilon j k1x plus B epsilon minus j k1x on one side of the barrier, and then we have this incident, and we have this f epsilon j k3x on the other side, the transmitted component. So then the transmission coefficient T is proportional to the square of the ratio between F and A. So that is T is the square of F over A, right? So if that is that, let's just assume in a simplified context that this is the same as this. And you recall the denominator of the ratio we just played with, which is cos K2D minus J K1 squared plus K2 squared over 2K1 K2 sine K2D, okay? So therefore, if this is the same as Z, so if we take the mod of this, mod squared of this, then we have cos K2D minus J K squared plus K all over 2K1 K2 sine K2D squared mod squared. And once evaluated, then we can take the mod of this where we don't need the complex operators. Then this will be the same as cos squared K squared D, which is the mod K1 squared plus K2 squared over 2K1 K2 all squared, then sine squared K2D. So that's the parameter, you know. So that T, the transmission coefficient, will now be the modulus of this expression, JK3D over cos K2D minus J K1 squared plus K2 squared over 2K1 K2 sine K2D, right? Squared, which is the same as 1 over Z squared. So it means that T is proportional to 1 over what we just resolved, right? K2 relative to this, right? Squared plus K1 squared plus K2 squared over 2K1 K2 all squared, then sine squared K2D, right? But if we bring this out, this is the same as K1 squared plus K2 squared over this 2 squared will be 4, K1 squared, K2 squared, okay? And now for very small potential, say delta V, which is the same as the difference between the potential relative to the two regions, would be approximately equal to H cross squared over 2M K2 squared minus K1 squared, right? Then delta V squared will be the same as H cross squared over 2M K2 squared minus K1 squared all squared. So the difference, E minus V1, will be approximately equal to H cross squared over 2M K1 squared. And then E minus V2 will be approximately equal to H cross squared over 2M K2 squared. And so by substituting these into the expression, we now see that T will be the same as 1 plus delta V squared sine squared K2D over 4 E minus V1 E minus V2 all inverse, which is the same as 1 plus H cross squared over 2M K2 squared minus K1 squared sine squared K2D over 4 H cross squared K1 squared over 2M into bracket h cross squared k2 squared over 2n. So once we simplify this, let's wipe this to make this look a little tidy. So this will be the same as 1 plus k2 squared minus k1 squared sine squared k2b over 4k1 squared k2 squared. Yes. And this matches the expression t equal to 1 over cos squared k2b plus k1 squared plus k2 squared over 2k1 k2 all squared sine squared k2b. Okay? So hence, the transmission coefficient is the same as 1 plus beta v squared sine squared k2d over 4 e minus v1 e, so e minus v2, and this is when v2 is less than e. Now, when e is less than v2, then we can use the Sanch operator or parameter, which is 1 plus, no, not lambda, delta. It's a small variation, v squared Sanch h squared alpha squared d over 4 e minus v1, then v2 minus e. Here, v2 is less than e, but in this case, e is less than v2. So you should observe the difference, okay? Observe the difference. Observe the difference here, okay? And then this is inverse, and then this is inverse.